Welcome back. We are continuing our look at the graphs of quadratic functions that we started in 2 videos ago. Okay, let's keep talking about these 2 graphs that we looked at earlier. Okay, so what patterns do you see in the tables of values you made next to graph A and graph B? So we go back up here. What patterns do we see? Well, in each case here, we're going up by 1 every time, right? -1, 0, 1, 2, 3, 4, 5. And here we go down 5, down 3, down 1, up 1, up 3, up 5. So you can see here odd numbers. Let's try this one. Again, we're going up by 1 each time here. This one is up 5, up 3, up 1, down 1, down 3, down 5. Same kind of idea, right? Here, again, it's the decreasing odd numbers as we go. So, in graph A, as x increases by 1, the y values increase or decrease, it depends, right, if they're adding or subtracting, by consecutive odd numbers. And actually this is also true for graph B, so I'm not even going to write something different here. It's really for graph A and B. There we go. Okay. Finding the vertex and axis symmetry. So something else we can use here. How can we know the x-coordinate of the vertex by looking at the x-coordinates of the zeros? So let's take a look here. Okay, here are the x-coordinates for the zeros, 1 and 3. There's the x-coordinate for the vertex, 2. Here are the x-coordinates for the zeros for graph B, -4 and 0. There's the x-coordinate for the vertex, -2. So, how are the x-coordinates for the x-intercepts related to the x-coordinate for the vertex? -4 and 0, the -2 there. The x-coordinate for the vertex is in the middle of the x-coordinates for the zeros. It's the midpoint. The x-coordinate for the vertex is the midpoint for the x-coordinate of the zeros. Or the x-intercepts, I should say. Or actually, they call them the zeros. Never mind, we'll say zeros. Okay? Or any pair of symmetric points. So you find any 2 symmetric points, find the midpoint, that'll be the x-coordinate for your vertex. Okay. What happens to the y values of the functions as the x values increase to very large numbers? What about as the x values decrease to very small numbers in the negative direction? Well, it depends, right? And that's really all up in this. So for graph A, we kind of wrote that in our end behavior here, but I guess we can rewrite it here. So for graph A, what happens as x goes to positive infinity versus what happens as x goes to negative infinity, right? What happens to our y values or our function values here? Well, again, we already kind of listed this, right? As x goes to infinity, that means as we go really far to the right, what happens to our y values? As we go further and further to the right, what happens to our y values? They're going to go up and up and up and up and up. So they go to positive infinity. Likewise, what happens as we go really far to the left? They're going to go up and up and up and up as well. So both go to positive infinity. Okay, whereas for graph B, okay, as same situation, as x goes really far to the right, or as x goes really far to the left, negative infinity, or positive infinity, negative infinity, respectively there. What happens to our function values? Well, as we go really far to the right, as x goes to infinity, our function's going down to negative infinity. As we go really, really far to the left, our function's going down to negative infinity as well. So in other words, both go to negative infinity. Okay? How can you know whether a quadratic function, the graph of a quadratic function, will open up or down? That's the lead coefficient. A is greater than 0, opens up like this. A is less than 0, open down, which is like this. Okay? Is it possible to determine the exact intervals that a quadratic function is increasing or decreasing just by looking at a graph of the function? And the answer is yes. Okay? Where are we increasing, where are we decreasing? Well, if you look here, right, it changes at the vertex, right? Increasing, then decreasing. Look up here. Decreasing, then increasing. And where does it change? At that vertex. Okay? So we need to know two things. Yes, you need to know the x-coordinate of the vertex and the lead coefficient. Okay? The x-coordinate tells you where the end behavior changes, and the A tells you, what kind of end behavior you're dealing with. Okay, remember that if A is positive, you're going to have opening up, which means you're going to increase from the vertex to the right, and you'll decrease from the left to the vertex like this. So this will be increasing, this will be decreasing. But if S is for A is greater than 0. But for A less than 0, your graph will look like this. Again, your vertex is here. You'll be increasing on this side of the vertex. There's your vertex for V. And then decreasing on this side of the vertex. Okay? All right, explain why the average rate of change of the interval from 1 to 3 for graph A was 0. We didn't do that one. We can do it now. I guess they kind of gave it away. So let's take a look at that one. From 1 to 3 for graph A is 0. Let's see what happens here. So from x equals 1 to x equals 3, why is this average rate of change or 0? 0. Well, it's because what are the y values doing? They're both the same thing. They're both 0 at those points. And so we're not going to have any change. It's because the y values are the same. Okay, you have the point 1, 0, and you have the point 3, 0. And if you do the slope formula, you'll have, m, which is stands for slope, right, is y2 minus y1 over x2 minus x1. You get 0 over 2, which is just 0. How are finding the slope of a line and finding the average rate of change on an interval of a quadratic function similar? How are they different? So similar, okay, both use the formula y2 minus y1 over x2 minus x1. Okay, different, well, because for the a line slope doesn't change, but a quadratic function quadratic function's slope does change. Can you graph a quadratic function if you don't know the vertex? Can you graph a quadratic function if you only know the x-intercepts? So we can graph a quadratic function if we don't know the vertex, but we would need to know some other points. Okay, help us find that. So yes, but we need additional information then. Okay, can you graph a quadratic function if you only know the x-intercepts? The answer to this one is actually no. Okay, because we don't know if the graph is stretched or not. Okay. Wow, remember that we need to know at least 2 points to define a unique line. Can you identify a unique quadratic with just 2 points? No. A quadratic requires 3 points to identify. And the explanation there, well, I mean, you can use the explanation here of the lines, right? That a line, that the zeros here was not enough, right? Can you graph a quadratic function if you only know the x-intercepts? Well, the most x-intercepts you can get is 2, so 2 x-intercepts isn't enough, and in general, you need 3 points. Oh, there, I just did that right there, boom. 3 points. Okay, next we'll do exploratory challenge 3.